Dear colleagues, let's start the second day of Science and Progress conference. And we start this day with plenary lecture and plenary lecture of Professor Gert Leux. I know Professor Leux is a really great scientist with interests in absolutely various directions. Professor Leux is a founding director at Max Planck Institute for the Science of Light. He is member of the Academy of Science Leopoldina, German Physical Society. He also member of European Physical Society, German Society of Applied Optics. I also want to tell you that Professor Leux is also a foreign member of Russian Academy of Sciences and honorary professor of Institute of Chemistry, St. Petersburg University. And I'm sure all of you will join me because on behalf of all the participants of Science and Progress conference, let's congratulate Professor Leux with election as a vice president of Society Optica. We most of all know this society as Optical Society of America, but now this is worldwide society. And it means that Professor Leux will be on duty for 4 years with this optical board. So I want to say that it's really a great honor to Science and Progress to have Professor Leux as a plenary lecture. And we really have a unique possibility to enjoy lecture of Professor Leux. So, Professor Leux, could you please tell us about this so interesting and important for everyone topic and your lecture title, what quantum physics has to offer for secure communication? Please.
Yes, thank you, Professor Mancina. Thank you for the introduction. You are too kind. So I'm sharing my screen. So I hope you now can see it. So you already read the title. So security has in communication has to do with the distribution of the cryptographic key. So this is the security bottleneck these days. And one problem nowadays is that people work on building a quantum computer. I'm sure most of you have heard about this. And a quantum computer, in not for all tasks, but for special tasks, can be much superior to a classical computer. And it is known that it will endanger the security, or it will kind of eliminate the security used in the public keys, which are most popular these days. So security can be based on complexity, and these public keys are security based on complexity, but it can also be based on physical laws, and this will be the main topic of my lecture. Security based on complexity means that you have algorithms which are asymmetric, where the computational complexity is asymmetric. And so in view of the being endangered by a potential quantum computer, people are now working on algorithms that give you security by complexity for which no attack by a quantum computer is known, and they are called post-quantum. So normally this acronym post-quantum, if you see this, it has nothing to do with quantum physics. It just means it's hopefully an algorithm which is immune against attacks by a quantum computer. One problem of there are already first solutions here, but it's extremely time consuming and takes much time to create a key. But in any case, there are some solutions here. On the other side, there are the physical laws, and in particular the laws of quantum physics, which can base the security not on complexity, but on fundamental laws. And that's a big difference, because complexity is always endangered, even if you have more powerful classical computers. So this has happened in the past. The lengths of keys has been changed during the last decades because computers became more powerful. If you base security on fundamental laws of physics, then you would not have to do this. And data could also be secure for a long time in the future. So what is this based on? Quantum physics. So quantum physics, so quantum security in communication, in short, quantum communication, is based on things like Heisenberg uncertainty, Einstein-Podolsky-Rosen Gedankenexperiment, quantum correlations. These are catchwords, and light sources that you use are quantum light sources like single photon sources, but also a laser puts out a coherent state, which is a pure quantum state ideally. And so this also falls into this basket. Why is it not proceeding? Okay. So before discussing practical aspects, let's look at what is so magic about quantum. I have all your pictures on the side. They were obscuring me, maybe not in your case, hopefully. Okay. So quantum physics basically is quantum wave mechanics. You have a Heisenberg's uncertainty relation, and there are so-called conjugate variables in quantum physics. There are different types. The most popular ones are position and momentum, x and p. And Heisenberg's uncertainty says that the variance of the of x, of the position, and the variance of the momentum multiplied together cannot be zero, this product. It has to be larger than a lower bound, which is connected to Planck's constant h bar. And then there is this famous relation, which is in a way the outcome of an experiment, that the momentum of a particle, when you look at it with enough detail, you see the quantum nature, and you see the quantum wave, so you can see scattering of electrons from graphite powder, for example. And then you see that these electrons are associated with the wavelengths, and the K here, maybe I switch on the laser pointer. Oh, wait a minute, why did it not do? Oh, here. Okay. So K is 1 over the wavelengths, or 2 pi divided by the wavelength. So the wavelengths is in here. So instead of using P in the uncertainty relation, you could also use K, the K of the matter wave. And then you have this equation delta variance of X and variance of K larger than 1/4. Because X has dimension position, and K, 2 pi divided by lambda, has the dimension 1 over position. This is dimensionless in this formulation. And so this applies to waves. So if you want to localize a wave, then you need a wide spectrum of K values. And this kind of looks familiar to us. We know this from classical physics. All this here is just to emphasize that often we cannot see the individual undulations, and we only see the envelope, like in the case of light. When you look at diffraction of light, you don't see the oscillations of the light beam, but you see the envelope, the intensity, which is like this red line. And we have ways to understand how this is probably due to interference, despite the fact that we cannot, in many cases, see these individual undulations. But this equation we know from classical physics. We have this for any wave, for light waves, for water waves. In water waves, we even can see the individual undulations. In most other waves, we don't see it so readily. And so there we have, there it is called space bandwidth product. So position space and position frequencies, for example, but this is not the only one. And basically the picture looks the same. You could also, instead of position and spatial frequencies, you could also have time and temporal frequencies, and then it's the famous time bandwidth product, delta t, the variance of t and the variance of omega larger than 1/4. So delta t basically is then the, so if you, then you would replace x by t, and then it would be the pulse duration. And just to remind ourselves, I have one picture to show, like for like a pedestrian approach, how can you understand this relation? And this is here, if you just have one oscillating frequency. So here, this is a temporal frequency, but the picture would look exactly the same if I would look at position frequencies and plot x here. That doesn't matter. So if you have a single frequency, then a single frequency means that basically you have a delta function, extremely narrow distribution in frequency space, which means that the delta k will be essentially 0. But in order to achieve this, you have to have an undulation which goes to infinity. Of course, I didn't show it here because I don't have enough space on my screen. So now if I add a second frequency, which is slightly somewhat different from the first one, and when I align the two maxima, then it would look like this. And if I add the two, because in waves you have the superposition principle, any wave, and you go for the sum, then they interfere constructively where the two maxima are aligned. And then there's also some partial constructive interference here. So you see the next maximum is smaller. So there is an envelope is starting to appear. And if we would continue to larger t, you would see that this goes further down. But instead of adding only one frequency, we can also add another 8 frequencies so that we have 10 altogether. And where in the middle, we make sure that the maxima are lined up. Then we have all these different frequencies and we add them up. And this is now octave spanning. So you can see the center frequency is the yellow one. I think probably the yellow is in the middle here. So the yellow comes back up here. And so some waves have half the period, so twice the frequency. Others have twice the period, so half the frequency. So it's like octave up and down. And then you get a more extreme interference, and you can see how a single pulse starts to appear. And if I do a more fine grain distribution with the same spread, then with 20 oscillating frequencies, you find it becomes even more narrow. The yellow one is the curve that we got with 10, summing 10 oscillating frequencies. So you can see how this, just for comparison, how going from here to here, how this narrows by a factor of 2 again. So this shows in a very simple way that as you have a larger and larger variance of frequencies, so a wider and wider spectrum, a wider and wider bandwidth, you can have a smaller and smaller variance in the time variable or the x variable if you're looking at waves as a function of x. Okay, so this we understand. Now, the question is, why is all this fuss about quantum physics being so different? What's different between this classical wave mechanics and quantum wave mechanics, apart from some mathematical details of the underlying differential equation? These are only mathematical details, they're not conceptually important. So the difference is this here. So here on the, I will explain on this slide. So quantum wave mechanics, we have this this envelope over the wave function, and this is what we want to measure if we want to get information about the quantum system. In a classical system, we have our wave. In the case of water waves, as I said, we can see the waves, but in other cases we cannot see the individual waves, like in classical, when we have classical description of light, and then we just see the intensity, which is the envelope. So this we want to measure. Now on the classical side, if we want to measure this, we can take a camera and take a picture, and we see the whole pulse, the whole distribution. In the case of water waves, we would even see the underlying oscillation here. And if we would repeat the experiment, it would be the same distribution. But on the quantum side, it's different. So here, the result of a position measurement, instead of giving this wide distribution that describes the system before measurement, you get just one value for the position. And then if you repeat the measurement, if you repeat the experiment, you get a different value. And you repeat again, you get another different value. If you repeat many times, then you build up a histogram, eventually you recover this distribution. So this is associated with the collapse of the wave function. Some people don't like this because it looks like some underlying dynamics, so they prefer the mathematical term or the projection, that you project onto a position eigenstate if you measure a position. And so the difference is the quantum measurement process. So in general, the quantum measurement process does not give the full information about the state of the system. Why do I say in general? So here, if we have such a wave packet and we measure position, then we understand that this wave packet is a superposition of many position eigenstates. There is a position eigenstate for a position of more to the left, more in the middle, more on the right, and many additional ones. And the superposition of all of them makes up this this wave packet. And when I have a measurement that measures position, you project onto one of them, but you don't know which one. So this is really truly random. So in all these cases, information is lost when you measure. In a single measurement, you lose this information. There is, I said in general, because there's an exception. If the system already before the measurement is in an eigenstate of the measurement operator, in our case, in a position eigenstate, then you don't lose information. The quantum wave before is in an eigenstate, and then the result of a position measurement is, of course, exactly this position. The same if an atom or molecule is in an energy eigenstate and you measure the energy, you get exactly the energy. But if you have an atom or molecule in a superposition of energy eigenstates and you measure the energy, you get with a certain probability one or the other energy, but you don't get all the energy. So what I described here with position is true for any measurement that we can do in quantum physics. So this is the difference. So how can we familiarize ourselves with the quantum measurement? So for a long time in my life, I thought, well, for waves, we have intuition, even the matter waves, we can use our intuition that we have from observing water waves, which we have done from our early childhood occasionally. But the quantum measurement process is something unique. Quantum, probably you cannot, there's nothing in real life that you can point to tell people, look, it's a little bit like this. And until I understood that our brain does something a little bit like this. So, I mean, this is only an analogy which is supposed to help us kind of come to terms with this bizarre effect that happens when you measure a quantum system, this projection or collapse of the wave function. And so here is a logo of a well-known car manufacturer. Of course, I shouldn't do any advertisement or reclam, but it's not from my country, as you recognize. So it's probably fair enough. And so this is a tricky logo, and I want to emphasize this by blocking the upper part. And now if you look at this center part here, nicely polished, so you see some reflection. So it's a frame and it's open to the left. It's so you can, it's from, so this is the back part, this is the front part. So it's clearly, it's a frame like this. Okay, you can see this. And if you block the lower part, it's also a frame, but it's pointing in the opposite direction. So I hope you can see this. So I'll pause a little bit. You can look at the other one, this one. So when you see the full thing, your brain can switch between these two positions. So this is a situation where the full information is both the frame looking to the left and the frame looking to the right. But the brain, in the brain, we can only see one at a time, but the brain can switch. So in a quantum measurement, the measurement also, if you measure a superposition, it measures only one component, but then the measurement cannot switch. Once it has done the measurement, that's it. You have to repeat the experiment, prepare this system again and do another measurement, and then it can be different. Well, in a way, it's not so different because as we keep looking at this logo, it's like a new experiment. Maybe it's not so different. To do this a bit more abstract, I showed you a cube here where we only see the edges. And this has the same ambiguity because we can look at this cube as such a cube. Now this is a cube which is not transparent. You only see the three facets which are towards you. And here the cube is transparent. So you can see this cube as if it were oriented in 3D like this, or if it were oriented in 3D like this. So if you only look at this one, I'm sure you can do this switching yourself. And I think this is the best way to understand how in a quantum system you can have a superposition of different informations, of different types of information. Whereas when you do the measurement, you only get one of them out and you lose some information. Okay. Entanglement is a superposition of more than one system. So, for example, you have three such cubes, and now, at least for me, it is such that when I, not 100% of the time, but most of the time, when I look at this cube and I see one of these orientations, then the other cubes appear in the same way. And then I can work on it in my brain and I can switch, but then more or less all three switch. And in a way, this would then be a superposition between three cubes like this plus three cubes like this, which is a famous superposition state in quantum physics. Well, I should say I took some time to go through this analogy, but don't take this analogy too serious. The brain and the logo of this car maker has nothing to do with quantum physics. It's only an analogy that might help. It gives you a hint of how to think about how you can, how it can be that you lose information when you do the measurement, how one can visualize this projection that happens in the quantum measurement process. Okay, so now back to quantum key distribution. Often one uses polarization states. So polarization is the, so light is electromagnetic wave with electric field and a magnetic field, and the polarization typically is determined by the direction of oscillation of the electric field. And we can separate different oscillation directions by a beam splitter. Such a beam splitting cube here can, for example, separate horizontally and vertically polarized polarization, polarized light. So this here is a horizontal vertical beam splitter. Suppose you have a single photon coming in. If it is horizontally polarized, it will go through and this detector will click. If it's vertically polarized, this detector will click. So the way to write this is, here is the horizontal vertical basis. And if we have a horizontally polarized photon, it's kind of oscillating in the horizontal direction. When it's vertically polarized, it's oscillating in the vertical direction. But of course, we can also go to different oscillation directions, and there are always the basis of linear polarization is always has two members which are orthogonal. So you can also go to a basis which is in the diagonal direction and anti-diagonal direction. It would look like this. So if we have a single photon that comes in with horizontal or vertical polarization, we will get clear signals. If the photon is polarized horizontally, this detector will click because horizontally polarized light will go through, will be transmitted. And then, of course, there will be no click on the other output port because a single photon can be the energy can only be measured on one side. The other possibility is that you send a vertically polarized photon, and this detector will click. But in this case, the horizontal detector will not click. Now, alternatively, if you put in a photon which has a polarization which is rotated by 45 degrees, so either anti-diagonal or diagonal, then you cannot tell the outcome. It can either be 0 or 1. So in a way, you could say in this HV basis, anti-diagonal and diagonal is a superposition of horizontal and vertical with a different factor in between, with a plus and a minus and some scaling factor. So then the measurement here will just pick one of them, like we just had it with the cubes, and we don't get the full information. So it will be very random. The outcome will be very random. Unless we tilt the polarizer by 45 degrees, then anti-diagonal and diagonal will give very deterministic values, because now the measurement operator, its basis, its eigenstates are anti-diagonal and diagonal, and then the quantum measurement will give a precise answer. But in this case, for H and V, it will be inconclusive. Okay, quantum key distribution. One uses just a limited number of different polarization states. I mean, there are other ways to do this, but the most popular are these polarization states, so I use this to describe it here. So one uses 2 or 4 different polarization states, and it's important that at least some of them are non-orthogonal. So to make sure that you not only talk about eigenstates of the measurement operator, so that you have superpositions with this ambiguity. So this is important. And each of these polarizations is then occupied by a single photon. So the first strategy is to prepare either of 4 states, H, V, A, or D. So this is the horizontal vertical basis in blue here. H and V are lined up, and A and D are superposition states in the horizontal vertical basis. If I would go to the anti-diagonal diagonal basis, then A and D would be basis states, single states, and then H and V would be superposition states. And so this is what you prepare and send to the receiver, and the receiver measures in the HV or in the AD basis. So if the receiver, he or she, measures in the HV basis, then you get precise values for H and V, but inconclusive data for A and D. And if he or she measures in the AD basis, you get precise values for A and D, but not for H and V. So for this to be secure, you have to have a random choice of bases on the sender side and on the receiver side. So how you make sure this is random? So this is a tricky question. So random numbers. So this this is a paper from my group. This is not the first paper in this field, but one that creates random numbers with a high rate. And the important thing is that when you use the quantum, so you can use the quantum measurement process as I described a few slides before, because you cannot predict the outcome. If you have a superposition state, you cannot predict the outcome of the projection that happens along with this quantum measurement process. And as a result, you have some randomness. And this randomness is unique, and that's an important point. It's unique if the quantum state is pure. That is, if it's not correlated with any other state. So this, there have been some papers on this. I don't go into the details here, but just to tell you, this is a very nice feature of creating random numbers through the quantum measurement process, that if you first determine that you measure a pure quantum state, then you know the sequence that you measure is unique. So there's no second other sequence with exactly this same numbers. Because in the classical case, this is not so clear. You can have a sequence and you can analyze the sequence for, is it really statistically uncorrelated? And so there are some tests with which you can do this. There are some of the tests I think are called Die Hard, Die Harder. They have some funny names like this. But when you have a single sequence, it may come out, this looks really very random, but someone else may have copied the sequence and looked at it. But if you look at a quantum state and create a correlated copy, this is like you're interacting from a different quantum a different quantum system has to interact with your quantum system, and due to this interaction you have entanglement. And if in an entangled system of overall system of more than one subsystem, if you then only look at a subsystem, this seems to be in a mixed state. So if the subsystem is pure, it cannot be part of a superposition state. That means you have really unique random numbers. So this is fine. Now you may ask the question, how does it really work if the sender and the receiver use random basis choices? So the sender uses either the HV basis or the AD basis, and the agreement is that if a sender uses H, it's supposed to mean 0. If you use V, then it's supposed to be 1, and if she uses A, it's supposed to be 0, and if she uses D, then it's supposed to be 1, and the sender switches between them. Now the receiver, of course, just sees data coming. What can the receiver do? He or she can also only do a random basis choice, and now if they happen to measure in the same basis, then the signal that the receiver measures, so this is a case where you have a unique, where you don't have a projection because you have a signal which is already an eigenstate in the measurement basis. So half the time when you have the same basis, you have the same numbers, so you have exactly the same sequence, and the other half of the time it's uncorrelated. So what to do? So after they have exchanged this information and the receiver does all kinds of measurements and accumulated some data, receiver and sender exchange the information about the choice of basis, not about the signal that the receiver measured, only which basis the receiver chosen. This information he sends to the sender. And she sends this, she sends back saying, in this case, not in this case, but also in this case, we have the same basis. So please discard all these cases where our basis is different. So they throw away half the data, and then they have a perfectly correlated set. So why is this secure against attacks? So the attack is typically by an unauthorized listener in the middle, which in the history of cryptography has always been called the eavesdropper. And so the eavesdropper, in order to get information, has to do a measurement. And you can already sense where this goes because the quantum measurement has these peculiar properties. So what can the eavesdropper do? I mean, basically, he, like the receiver, has to make a random basis choice. So the eavesdropper uses a random basis choice. Half the time, he happens to choose the same basis as the sender was using to send the 0 or 1. And in this case, he gets perfect data. The other half of the time, he uses the wrong basis. So then sometimes it's right, sometimes it's wrong. So in the case when you have the wrong basis, half the time you get the right signal. So half the time you get the wrong signal. So it means overall in 25%, 1/4 of the times, he gets the wrong signal. So this is an error rate. So the eavesdropper can do nothing but take the data that he or she measured, and it will be wrong in 1/4 of the cases. And then he can resend this signal to not show his presence, his or her presence. And then the receiver will measure, and the receiver, not knowing about the eavesdropper, will communicate with the sender, and they kind of determine when did we have the same basis in this random basis choice after the fact later. And then they agree on the data set when they should have exactly the same signals. And then they can sacrifice part of these data and check, do we really have the right signal? Of course, this will be communicated on a public channel, so this cannot be used for cryptography, but it's used for checking. And then if there's an eavesdropper, in 25% of the cases, the receiver will have the wrong signal. So by detecting that they don't have this strong correlation that they were supposed to have, they know something's going wrong. So most likely there's an eavesdropper in the middle, so we don't use the data. So you cannot avoid the eavesdropper, but you can detect the eavesdropper. And if they have perfect correlation, they know that it is impossible that an eavesdropper has got some information about the signal, an eavesdropper which is somewhere in the middle of this communication channel. So this basically, how am I doing time-wise? There's something in the chat. Should I read this? Maybe Alina, you could look in the chat if there's something I should do in the middle of my talk. Let me know. Okay, so this was the first strategy. I meant to say that this scheme with these 4 states is the famous BB84 protocol, named after Charlie Bennett and Jill Brassard from '84. So this was the very beginning, and the field kind of started to blossom in the last 30 years. So sometime in the 90s, middle and end of the 90s, more and more people became interested in this. And now it's a huge, fairly large community worldwide. So I told you about one strategy where you have 4 states and these 2 bases. It's also possible to use just 2 states, but then of course these 2 states should not be orthogonal. So they are, if you use polarization, these 2 polarizations should not be different by 90 degrees. So here I chose 45 degrees. I mean, the numbers, you can use any numbers. The most important thing is that these are 45 degrees apart. This is also a protocol that goes back to Bennett. So in this case, it was a paper with a sole author, Charlie Bennett. So this is the B92 protocol. So if the single photon is polarized in one direction, it's a 0. If it's polarized in the other direction, it's a 1. So these white arrows are, so this 22.5, this would be the 0, and this would be the 1, the white arrows, if you have one or the other. Now you can again use two different bases. And in order to do this so-called unambiguous state discrimination, where you want to have 100% good data, so the best you can do, this is what people have discussed and discovered. There is a tutorial review on discrimination of content states by Janos Bergu about 10 years ago here. And of course, there are many other papers, but this is one which is good to look at. So the best strategy here, what you can do is choose two bases, either the red basis, the bases of course are 90-degree bases, or the blue one. So in the red one, if you have, if you measure a 65 is the 1. If you, in the red basis, you measure a 1, then it can have been a 1 or a 0, because both these white arrows have a non-zero projection when you're projecting on this 67.5 degree basis, the basis for the 1 bit. But if in the red basis you detect a photon in the minus 22.5 direction, so these are the output ports of the polarizing beam splitter, then you know it must have been a 0, because the white one, is at right angles to this basis, so that can never give a signal. So in some cases you have 100% certainty about the state, but if this one clicks here in the red basis, you don't know. So you have inconclusive results. So you can have 3 results: conclusive result in the red basis, or inconclusive result. And then you go to the blue basis, and it's the same thing. You can get only then you can be sure about, so here you can be sure about the 0, and the blue basis you can be sure about the 1. So there you also have secure information or inconclusive information. You have these 3 possible outcomes. This is unambiguous state discrimination. And then there is something called minimum error discrimination. Again, you have 2 polarization states which are non-orthogonal, which would then be also 0 and 1. And now, so this is why I chose these odd directions for the polarization, which are 45-degree different. If I now use the HV bases, then I always get some information, because the projection of the white, the one white or the other white state, so the 0 or 1 bit, will give a finite probability both on the V and on the H axis when you do the projection. But the probability to see the 1 bit is much higher. So if you have a vertical outcome, a vertical signal, then with a much higher probability, it was a 1 bit, 67 is the 1 here. And if you have a signal at the horizontally polarized output with a higher probability to, you have a 0 bit. Now you get some information every time, but you have error. It's not, you cannot be 100% sure. But this information, but you have some information advantage, and this is a bit more tricky. So I will not go into the details here, but this you can also use to extract a secure key. Oh, I think I forgot to say that the joint signals, which are the same between receiver and sender, this is basically the key that is then used in cryptography. Okay, so the last slide on this topic, minimum error discrimination. This is we discussed about with single photons. You can also do this with coherent light, coherent state. So basically you can use lasers, attenuated lasers. And there we have coherent states in phase diagram where you have amplitude and phase. So we have this 2-dimensional plot. and the quantum uncertainty gives you a finite blob, a finite distribution. And now if you have two coherent states which are non-orthogonal, so these are two Gaussians which have partial overlap, then these are two non-orthogonal quantum states, and this means that you can do quantum key distribution with them using this minimum error discrimination. And so this is using amplitude and phase of a mode, or also in the case of these coherent states, you can gain from using polarization. And when you have polarization, basically polarization means you have two modes, and you have the Poincare sphere and the Stokes parameters. In the case of two coherent states in one mode, now in the polarization basis, it will be two states on the Poincare sphere, and even here you have a choice to of course also have more than these two states, but two states would suffice already. The advantage of the polarization basis here is that then the measurement is simpler. In this case here, you have to measure phase, you have to be phase sensitive, so you have to use local oscillator, and in the polarization this is kind of like a built-in quantity. So we have used this a while ago to do a transfer along a free space link from the old building of the Max Planck Institute for Quantum Optics and the Computer Science Department. So looking from the roof here, this is you see the roof of the upper floors of the Computer Science Department of the University in Erlangen. And so this was, what was it, 1.6 kilometers here it says. And this was done with 4 different polarization states. And basically what we studied is what kind of noise does the atmosphere introduce. And since the atmosphere is not birefringent, these polarization states survive. This is also an advantage of the polarization with respect to just using amplitude and phase, because phase is obscured in by the fluctuations in the atmosphere. When you want to go to longer distance, there is a problem, because the direct link through the air is not so easy. The alternative is to use fibers, but fibers have losses. So if you look at some longer distance, so this would probably be maybe 3,000 kilometers. So this would go from maybe slightly south of Moscow to Lisbon. So this is quite a long distance, so this is not so easy. And so some people have thought about using satellite link. So you could either have some low Earth orbits or high Earth orbits. If you go to very high orbits, then you can have a geostationary satellite. But of course, this is at what is it, around about 40,000 kilometers, at an elevation of 40,000 kilometers, whereas the Earth has 7,000 kilometers. So this is somewhere down here, like here. So this is so this is really long distance. So first you might think, oh, but then the distance is much longer. How can it compete with this much shorter fiber? And it can compete, and this is because in the fiber you have an attenuation which is exponential. So if you have a certain, if you have loss gamma in 10 kilometers, then in 20 kilometers you will have a loss gamma squared. So the length appears in the argument of the exponent, in the exponent of the so in the exponent here. So for the best possible fibers, the attenuation is such that you lose 90% in 50 kilometers about in the fiber. Whereas if you go to the satellite, so the atmosphere is only the first few kilometers, you can almost neglect. Then this is free space, so there's no absorption. So the problem is completely different from the problem in the fiber. Here, the problem is not that you absorb light, the problem is that you have diffraction limited growth. And if you like send the clever thing is to send light from the satellite to the Earth, because then the atmosphere does not change the propagation. And then it depends on the aperture, how big an aperture you can have on Earth here. So if you have a given aperture and you go further and further away, then the diffraction limited spread will become larger and larger. And so you lose because you don't collect all the light. And this, the way you lose goes as inverse square of the length. And this is much slower than this exponential scaling. So L to the -2 is scales much more favorable than 10 to the -L. There are worlds between the two scalings. So if you allow for 50 dB losses, then in a fiber, in the best fiber, you can go 250 kilometers. Whereas in geostationary case, if you use collection, if you use a aperture of 60 centimeters, you would go to 50 dB. And then it doesn't matter. I mean, only if you go too far on the side of the Earth, maybe because then you go longer through the atmosphere, then you will have it's probably difficult to go from two opposite sides on the Earth, but somewhere here. So this is 40,000, this half around the Earth will be 20,000, so 10,000 or surely 5,000 kilometers, you should easily be doable. So in practice, you can have, instead of a geostationary, you can also have a low Earth orbit, but then the satellite will be moving, but this is also a possibility. Then the length will be smaller and it will even be more favorable. So the Chinese have done an experiment with a dedicated quantum satellite, very famous, nice experiment. Satellite was called, the project was called Meteos, I think. But about a year before they did this experiment, so they actually exchanged the cryptographic key. So we didn't do this, but about a year before they launched their satellite, we used an already existing satellite, AlphaSat. It's a European satellite, which was built in Germany. And without going to the satellite, we could use this satellite to check the quantum properties of the channel, because when we use these coherent states instead of single photon, then what you have on the satellite is all the components that you need. So the quantum communication with coherent laser light, the technology, the components are very close to what you have in coherent classical communication. So AlphaSat is such a geostationary satellite. So on this AlphaSat, there is this laser communication terminal. And here you can see there's these cardanic mounts, so it can point in it can be adjusted to point in the direction of the ground station. So this worked quite well. At the moment, and this is my last slide, I'm involved in a big consortium between two Fraunhofer institutes and the one institute of the German Aerospace Center, called DLR in German, and our Max Planck Institute. And this is about an implementation of quantum key distribution in the real world. So the German government is giving money for this. There are already commercial projects. For example, ID Quantique in Geneva sells commercially quantum key distribution devices, and this is for a point-to-point fiber link. But here in this project, we try to adapt everything to the real world, because maybe you need to combine free space and fiber, and you want to use existing fiber. And so we explore to some extent also the more engineering aspect. So it's a combination of further fundamental studies combined with engineering aspects and development. So it's a fun project. Okay, with this, I come to the end. Thank you very much. Maybe you have some questions. Oh, I took too much time. Hello?
Professor Leix, I don't, can you hear me?
Yes, now I can hear you, yes.
Yes, because I don't hear Alina, Professor Manshina. Are you here, Alina? But in the meanwhile, may I ask you a question?
Yes, yes, sure.
Yeah. So it was really very exciting talk, and it is really exciting to know that this physically based algorithm may be now implemented to our everyday life devices. It's really very exciting. But I have a particular question. When you talk about the creating random numbers, how can you ensure if the quantum state is pure or it is correlated? I mean, in reality.
Yes, that's a good question. Thank you. If you are if you talk about a quantum state in a single mode of the light field, so there are ways to check whether a state is pure. So in the case of I give you an example. In the case of a light field, you can measure the distribution function in. So you don't know the state of the light. You have to do measurement to determine the light field. And so you have to, so you can measure the phase space distribution function. So it's this distribution function in this space where you plot amplitude and phase, so to say. I had, in one case, I showed such a frame. And there are different, in quantum physics, there are different types of phase space distribution functions, because these two quadratures, so what you plot on the two axes, these are these conjugate variables like x and p, omega and t, so they don't commute. They have this Fourier transform relationship to each other. And so if you do a measurement, so which type of distribution function you get depends on the measurement. So if you do a particular measurement, then you get the so-called Q function or Rossini function. And this is very well suited to determine whether the state is pure or mixed. And so it's so for a mixed state, the Q function has a clear maximum. So in other words, you could also say that in this phase space, if so, the phase space distribution function can never be a two-dimensional delta peak, because there is some minimum extension because of Heisenberg's uncertainty. That Heisenberg's uncertainty, this Fourier relation, Fourier transform relation, gives you a finite area in phase space. And if you are at the minimum value for this finite area, then you know it's a pure state. If you have another mode of the light field being correlated with this one, the two states together, they can be in a pure state. But if you look only at one of them, then it will be more noisy. And then if you measure only one of them, you will see a wider distribution. So this is, so there's a clear, so in the case of light field, it is obvious. In more, if you ask the case in more general, how can I be sure that a quantum state is pure? The type of measurement you have to do is surely different in different systems. But in the case of light fields, I know how to do this.
Okay, thank you so much. I had a call from Professor Manchin. She had got problems with Zoom, so I'm sorry. So I will take your duties of the chair of this session. So,
okay.
Dear colleagues, do you have questions to Professor Bex? Well,
so either my talk was too simple or it was too complicated.
It was excellent, just excellent.
Thank you.
Okay, so Professor Lex, thank you so much for this really bright lecture. I hope we all enjoyed it, and so we are very grateful to you for this. And now we should, yes.
Thank you very much.
Thank you so much. So now we should finish this plenary session and we go to our sections.